Hello friends, welcome back to Physics with Ben. This is a continuation on the video series on the theory on Hooke's law. If you're just coming in, you may love to click in the description box to watch the first part of this video where I stated the Hooke's law. I also explained elasticity, elastic material. We drew a graph of Hooke's law and we explained the meaning of the graph and all the parameters that are involved in the graph. You may love to click in the description box below to also find the video link for all the calculations under the topic of Hooke's law. Don't forget to like, comment, and share this video. Also subscribe and click on the notification bell so that I can get due notification anytime I upload a new content. Without wasting more time, let's go straight to the business of the day. The Young's modulus. The Young's modulus is defined as tensile stress. Is defined as tensile stress all over tensile strain, whereas tensile cancel out tensile and you are left with stress all over strain. But stress is given as the ratio of force to the cross-sectional area. This rubber band has a cross-sectional area. What we are trying to say here is that increase in the cross-sectional area will cause a decrease in the stress and vice versa. So we write that, and the unit of this is Newton per meter squared, and the strain is given to be extension all over the original length. Strain, however, is a dimensionless quantity, and then it has no SI units. So we define the Young's modulus as force divided by area divided by extension all over load. If you evaluate that correctly, you have the Young's modulus as force over area times L all over E. Therefore, the Young's modulus is defined as force times extension all over area times length times force over original length all over area times extension in the units of Newton per meter squared. That is the definition for the Young's modulus. The next thing we want to look at quickly is the work done. The work done in stretching an elastic spring. If I stretch this spring from both ends, the work done in stretching this spring, also known as the elastic potential energy stored in the spring. In this topic, you also love to know that the law of conservation of energy is applied in this topic. The law of conservation of mechanical energy, where the kinetic energy is equal to the potential energy of the spring. So we write that. Are we good? Yes, we are good. So the work done in stretching a spring is given to be W is equal to the average force times extension. You recall that extension is higher than the distance. And then, but the average force is given to be initial force F naught plus the final force divided by 2. What do we mean by that? If you can observe very well this spring here, at this point no force is attached to the spring, so the force is 0. What you have here is just the mass of the spring. By the time you attach a force, in this case, these are masses, but we can convert them to forces by dividing this are 1, 2, 3, 300 grams divided by 1000 kilograms times 10 give you the force. So when you apply a force here, the spring will stretch down. So we say that the initial force is 0, and so this is the same thing as 0 plus the final force divided by 2. So we write that the average force is given as final force divided by 2. You can call this your equation. The equation for the young force was equation number 2. This is equation number 3, and this is equation number 4. So we write that the work done is actually equal to F over 2 times the extension. Call this equation number 5. You see it as Fe over 2, the same thing. But recall that from Hooke's law, that F is equal to K times E. So we are going to substitute the whole of this in place of F in equation number 5. So this implies that the work done in stretching the spring is given to be Ke squared all over 2. Can call this equation number 6. Remember that the work done in stretching the spring is also known as the elastic potential energy of the spring. And from the law of conservation of mechanical energy, we write that this work done is equals to the elastic potential energy of the spring. And this is also equals to the kinetic energy of the spring. If you stretch this rubber band and release the screw, you have done something that looks like this, that your PE is equals to your KE. And in this case, what we are trying to say is that our work done is equals to elastic potential energy is equals to Fe all over 2, and is equals to Ke squared all over 2. And you know that kinetic energy Ke is given to be half mv squared. So you are free to say that from the law of conservation of mechanical energy, we write that this is Fe, we write that Fe all over 2 is equals to Ke squared all over 2, and is equals to what? Half mv squared. That is from here. From PE is equals to Ke. So what this means is that from here we can say that Fe over 2 is equals to what? Is equals to Ke squared all over 2. They may give you an equation where you have to apply this. I'm going to make a video on what I call the physics of cut and join. This is probably another equation here. So you can write this as equation number 7. Again, this also means that your Fe all over 2 is equals to half mv squared. You can call this equation number 8. Also, your Ke squared all over 2 is equals to half mv squared. You can call this equation number 9. So these are all possible equations under Hooke's law. In summary, let's write these equations so I don't forget them. They are very, very important equations. We have the first one as F is equal to KE. We'll look at this later. F is KE, that's equation number 1. For the Young's modulus, again, K is equal to F all over E. Equation number 2. The Y is equal to force times L all over A times extension, the Young's modulus. This is equation number 3. We also have work done is equal to average force times extension. Equation number 4. We also have average force is equal to initial force plus final force divided by 2. Equation number 5. We also have work done is equal to Fe all over 2. Equation number 6. We have work done is equal to Ke squared all over 2. Equation number 7. These are all equations. I want that you're interested to know that we have used all these equations in the other videos. So just we copy them down and then work on them. The other one is we have from here we say that this same work done is equals to Fe all over 2 is equals to Ke squared all over 2. Call this equation 8 star. Yes, equation 8 star. And then we say that here you also have your Fe all over 2 is equals to Ke squared all over 2. Call it equation 9. And then from the law of conservation of mechanical energy, we say that Fe all over 2 is equals to Ke squared all over 2 is equals to half mv squared. And this is congruent to Pe, elastic potential energy, is equals to what? K kinetic energy. We say that a stone of mass this was released from a catapult. Calculate the velocity of the stone, or the instantaneous velocity of the stone. This is the equation you are going to make use of. So from here we write that you have you have Fe all over 2 is equals to half mv squared. You have Ke squared all over 2 is equals to half mv squared. So this is equation 10. Equation what? 11. So without wasting more time, let us look at something different from this. So we have looked at the energy stored in the spring and also the elastic potential energy of the spring. So they were asked to state the law of conservation of mechanical energy. In this case, we state that when you stretch a catapult with a stone, this is how you state it. Energy in a closed or isolated system, mechanical energy is not lost, but transformed from kinetic to potential and potential to kinetic and vice versa. And that is the law here. This particular equation is just what I just stated. In a closed or isolated system, mechanical energy is not lost, but it is transferred or transformed from elastic potential energy to kinetic energy. or from kinetic energy to elastic potential energy, and vice versa. So you can use any of this based on how the equation is structured. We want to look at an equation, extension for an elastic spiral string by a force. Right. Extension of an elastic spiral spring by a force. Good. From the beginning of this class, we have been playing with this. There is a lot of physics behind what we are seeing here. And right now, I'm going to deduce the equations to explain this. This spiral spring is extended by this force. What are the equations that are controlling this? We write that, recall that the tension T is given to the mass, that's gravity, and this is written as Kx. Call this equation number 12. Equation number 12. Good. For equation number 12, we can still write that our L, let L be equal to mass of m all over x. Call this equation number 13. Good. So from here, the T stands for the extension. When you introduce a mass to this spring, you introduce a tension in the spring that stretches the material, the spring, from its original length to a new length. And tension and force, they are measured in the SI units of Newton. So this equation you have seen here, equation 12, is the same thing as equation 1, where T and force are the same. And in this equation, X is the same thing as E. They are all measured in meters. All of them stands for extension. So we can write that from equation 12, we can write that mg is equals to kx. Call this equation 12a. Equation 12a. Now, equation 13 can be written as follows. As m is equals to lx. Call this equation 13a. Equation 13a is a very, very important equation that will be used in our next video. Which is experiments on Hooke's law. I'm coming to that, where m, equation 13 looks like this. Y is equals to mx, like a straight line equation. M, the mass, the slotted mass of the spring, and then the L is the L in this case stands for the stiffness or the softness of the material. L in equation 13 is the same thing as K in equation 1. K and L have the same meaning in this equation. So when you see them in various textbooks, don't be confused. So we write that X and E also stand. So equation 1 and equation 13, they are the same. That's what I'm trying to say in this talk, in this video. So the examiners may ask you to oscillate this spring and find the time for 20 complete oscillation and plot a graph of the masses against the period of oscillation. How do you go about it? From T is equals to 2 pi root root m plus m naught. Root m plus m naught all over Lg. We call this our equation number 14. Equation number 14 is the equation that explains the physics behind everything you are seeing here. M stands for slotted masses, and M naught stands for the mass of the spring. If you weigh this on a spring balance, you will record that the mass will be like 0.5 gram. That is the mass of the spring. And then L stands for the extension. If you put a mass here, it will extend, and that extension is the length L. And G stands for the association to gravity, the force of gravity acting on the spring, on the masses in the downward direction. That is the meaning of that. And then T stands for the period of oscillation, the time it takes this to go up and come down in a particular number of oscillation. And 2 pi stands for the angle in radians that this spring makes to go up and down. Recall that when you go 360, when you move around the circle, that is 360. So when the spring goes up and comes down, this is equivalent to 2 pi in radians, and this is equal to 360 degrees. That is the meaning of the pi, of 2 pi in this on the board here. So we are going to generate an equation that will help us plot the graph of m against t squared. From here we write that t divided by 2 pi is equals to the root of m plus m naught divided by L times G. I would love to clean this, so I'll transfer my equation down here. We write that equation 12, we have our t is equals to n times g is equals to kx. We have our L is equals to m over x. This is equation 12, equation 13. We have our mg is equals to kx, equation 12a, and we have our m is equals to lx, equation 13a, and then we have our t is equals to 2 pi root m plus m naught divided by lg. So we write that from t is equals to 2 pi root m plus m naught divided by lg, which is equation 14, which is our equation 14 here. Good. We have t over 2 pi is equals to the root of m plus m naught divided by lg. So this is the same thing as t over 2 pi. T over 2 pi is equals to m plus m naught divided by lg, all raised to the power 1 over 2. So we square both sides. So rather t over 2 pi all square is equals to m plus m naught over LG is equal 1 over 2 times 2 times 2. So this becomes this, we have t squared all over 4 pi, all over 4 pi squared is equals to m plus m naught divided by LG. So we cross multiply, so we have 4 pi squared into m plus m naught is equals to t squared LG. We clear the brackets. We have 4 pi squared m plus 4 pi squared m naught is equals to t squared LG. So we have 4 pi squared. We're going to make m the subject of the formula. So we have 4 pi squared m is equals to t squared LG minus 4 pi squared m naught. So we divide both sides by 4 pi squared. 4 pi squared. 4 pi squared. 4 pi squared. So that this will go, this will go, this will go, this will go. So that we have our n is equals to t squared LG all over 4 pi squared minus m naught. We rearrange this equation. Good. We have our n is equals to LG over 4 pi squared dot t squared minus m naught. So we call this, let me rewrite this very well, dot t squared minus m naught. Call this equation number 15. Equation number 15. So equation number 15 is the equation we are also going to use to plot a graph. So M stands for the slotted masses, and L stands for the length extension of the spring, and G the acceleration due to gravity, and T squared stands for the period of oscillation of the spring, and then M naught stands for the mass of the spring, the unloaded spring, where this equation looks like a straight line graph equation that looks like this. This is your y is equals to mx minus c. In this case, Lg over 4 pi square, Lg over 4 pi square is the slope of the graph, and the t square is the value to be plotted on the x-axis, while m naught, which is the mass of the unloaded spring, in this case the negative intercept on the positive negative y-axis. So these are all the equations we have in this topic. To this we have come to the end of this video. Don't forget to subscribe, like, comment, and share. Look at all these equations. I am deliberate writing them this way, beginning from equation number 1 down to equation number 15. The equations we are going to make use of in plotting graph in the next video. Equation number 15, we make use of equation number 15, equation 1, equation number 13, m is equal to lx. So take notes and see you next in the next video series, where we shall be looking at the experimental aspects of Hooke's law. Don't forget to subscribe, like, comment, and share this video to the ladies. God bless you. Bye. Bye.